The last type of titration curve we're going to look at calculating is that of a diprotic molecule. We could extend this to polyprotic in general, but the general idea will be present with a diprotic system. And so this is you'll get experience with this in the class if you, depending on when the lab falls this year. So what we're going to look at is with the diprotic molecule, we will have two equivalence points. Our titrant is always going to be a monoprotic strong acid or strong base, so we don't need to worry about that. But essentially, if we think about our acid is, say we have a diprotic acid, we're titrating with the weak base or strong base. We have our H2A, that's going to react with hydroxide, and our first equivalence point will be removing the first proton, which will leave us with HA plus water. And then we'll have a second equivalence point where we have all the HA, will react with the hydroxide, and we'll form our A2 minus plus water. So each of these will give their own distinct equivalence point. One will probably be more obvious than the other in terms of actually observing the equivalence points, and you'll see this in some of the data we look at and that you look at in the lab as well. So let's look at how we would handle calculating what's going on at these different points of a titration curve. So let's imagine we have an imaginary acid or base here. This is based on a figure that's in your textbook. So let's titrate a diprotic weak base, and we need to know its pKb values. So we'll have pKb1 is equal to 4, and pKb2 is equal to 9. The equivalent Ka values, pKa2 is equal to 10, not 1, but 10. And pKa1 is equal to 5. Okay, so let's imagine we have a small volume, 10 milliliters of our base of a 0.1 molar solution. We'll call it B. And then we're going to titrate with, again, 0.1 molar HCl. So we'll stick with our usual concentration here. All right, so what this titration curve is going to look like, we have here, is we're going to have some things going on. So let's just sort of introduce what's going on. So we'll have our initial concentration, our initial pH. That's here point A, and that will be a weak base, right? That's present in solution. Now it's a diprotic weak base, but it's the fully basic form, the fully deprotonated form. So we can treat that like we would a monoprotic weak base. So we can say use Kb1 is going to be equal to x squared over f minus x, right? This is the formula we'll use where x is equal to concentration of hydroxide to find the pH at this point. Then here in between the beginning point and the first equivalence point, we have a buffer because we're going to have A minus and HA. Sorry, let me be consistent in my A2 minus plus HA minus. So the fully deprotonated form and the singly deprotonated form will both be present. And that's going to form a buffer. We'll reach the equivalence point, and we'll have a solution of just the intermediate form, HA minus. Then we'll have a second buffer region here. And in that buffer region, we'll have HA and H2A that'll be present. I think I've changed my terminology here, but we're sticking with this. And then we will reach the second equivalence point where everything has now turned into H2A. Okay, and so we can treat the pH of this we're going to find as a solution of a weak acid. So it's a diprotic weak acid, but right? We just need to worry about that first deprotonation to find the pH, just like we talked about in the previous chapter. And so we can use Ka1 is equal to x squared over f prime minus x, because our concentration has changed. And again, in here, x is going to be equal to the concentration of H plus, because now we're considering an acid. And then here is just, we're going to have excess titrant that will control what's going on in terms of the pH. Okay, so in the next couple videos, we'll go through this example calculation with the values that I provided previously to find what is the pH. And you can read it off of the chart, but we'll show how to calculate it.